Hello there, and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Tonight, we're drifting through the ethereal world of the aurora borealis, the northern lights. These celestial curtains have whispered across Arctic skies for millions of years, painting darkness with ribbons of green, blue, and violet light. But beneath their beauty lies a collection of gentle truths, soothing facts, and quiet wonders that will carry you softly towards sleep. If these peaceful explorations help you unwind or give you a moment of calm in your day, consider liking and subscribing to the channel. It helps other weary souls find their way here too, one sleepy seeker at a time. Now, let yourself get completely comfortable. Take a slow, deep breath, and let's begin this gentle drift through the most relaxing fact about the Northern Lights. The Northern Lights are born from the breath of the sun. High above our planet, 93 million miles away, the sun releases a constant stream of charged particles into space. This solar wind, invisible and silent, travels at speeds of over 1 million miles per hour. When these particles reach Earth, they encounter our planet's magnetic field, a protective bubble that surrounds us like an invisible embrace. Most of these solar particles are gently deflected away, but some slip through near the magnetic poles, where the field lines converge like the threads of a cosmic web. As these particles enter our atmosphere, they collide with gases floating in the thin air 60 to 400 miles above the surface. Each collision releases energy in the form of light, creating the aurora. It's not violent or chaotic. It's a gentle dance between the cosmos and our atmosphere. A quiet conversation written in photons across the dark canvas of the polar sky. The colors of the aurora tell stories of altitude and atmosphere. Green is the most common color, appearing when solar particles collide with oxygen atoms about 60 to 150 miles above Earth. This soft, glowing green has been described by countless observers as otherworldly, like silk scarves flowing in a breeze that doesn't exist. Higher up, around 150 to 300 miles above the surface, oxygen creates red light, though this crimson aurora is often too faint for the human eye to detect. Blue and violet hues emerge when particles strike nitrogen molecules, creating colors that shift and shimmer like watercolor paint, bleeding across wet paper. These cooler tones often appear at the lower edges of aurora displays, closer to Earth's surface where nitrogen is more abundant. The entire spectrum dances together in combinations that never repeat exactly the same way twice, making each aurora display as unique as a fingerprint written in light. Ancient cultures wove the Northern Lights into their deepest stories and beliefs. The Inuit peoples of Alaska and northern Canada saw the aurora as the spirits of those who had passed away, dancing joyfully across the sky. Some believed the lights were torches held by spirits to guide new souls to the afterlife. In Norse mythology, the aurora was thought to be the reflection of light bouncing off the shields and armor of the Valkyries as they rode across the heavens. The Sami people of northern Scandinavia called the lights revontulet, meaning foxfires. According to their legends, a magical Arctic fox ran so quickly across the snow that its tail swept up snowflakes and flung them high into the sky, where they sparkled and glowed. Finnish folklore tells of the firefox whose fur created sparks as it dashed through the forest, sending these sparks up to paint the sky. These stories, passed down through generations around fires and under star-filled skies, reflect humanity's deep connection to this natural wonder. Long before science explained the aurora, people looked up and saw magic, spirituality, and the sacred dance of forces beyond their understanding. The northern lights follow patterns that mirror Earth's magnetic field. Our planet's magnetic field isn't uniform like a simple bar magnet. Instead, it's dynamic, shaped by the spinning molten iron in Earth's core and influenced by solar activity. The aurora appears in an oval shape around each magnetic pole. Called the auroral oval, this invisible ring expands and contracts based on solar conditions, sometimes stretching as far south as northern United States. During periods of high solar activity, the auroral oval isn't perfectly centered on the geographic North Pole. Instead, it's offset toward the magnetic North Pole, which currently lies in northern Canada and slowly wanders over time. This means some locations, like northern Alaska and northern Scandinavia, sit directly beneath the auroral oval and see the lights frequently. Other places must wait for geomagnetic storms to push the aurora farther from its usual haunts. Solar storms can make the northern lights visible in unexpected places. When the sun releases particularly strong bursts of charged particles, called coronal mass ejections, the aurora can appear much farther south than usual. Historical records describe aurora sightings as far south as Rome, the Caribbean, and even Hawaii during extreme solar events. The most famous of these occurred in 1859. Known as the Carrington Event, telegraph systems failed worldwide, with some operators receiving electric shocks from their equipment. But the aurora was visible across most of the United States and Europe, so bright that people could read newspapers by its light. Gold miners in the Rocky Mountains woke up thinking it was dawn because the sky glowed so brilliantly. These extreme events remind us that Earth exists within the sun's sphere of influence, connected by invisible threads of magnetism and solar wind. Even in our modern world of artificial lights and indoor living, we remain part of a vast cosmic system that occasionally makes its presence known in the most beautiful ways. The northern lights make sounds, though scientists debate exactly how. For centuries, people living beneath the aurora reported hearing faint crackling, hissing, or whooshing sounds during particularly active displays. Many researchers dismissed these accounts, arguing that the aurora occurs too high in the atmosphere to produce audible sound waves that could reach the ground. Recent studies suggest the sounds might be real after all. Some scientists propose that the electromagnetic fields associated with the aurora could cause objects on the ground, like metal fences or even individual hairs, to vibrate and produce faint sounds. Others theorize that very low-frequency radio waves generated by the aurora might be converted to sound by certain materials or atmospheric conditions. Whether these auroral sounds exist or not doesn't diminish the profound silence that accompanies most aurora viewing experiences. Standing beneath the northern lights typically means being far from cities, in places where human-made noise fades to nothing. The aurora dances in a cathedral of silence, broken only by the whisper of wind across snow or the distant howl of Arctic wildlife. The lights appear to move, but this is partly an illusion. When you watch the northern lights, they seem to flow and dance with purposeful movement, like cosmic choreography performed on the largest stage imaginable. Some of this movement is real as solar particles stream into different parts of the atmosphere, and magnetic field lines shift and reconnect. But much of the apparent motion is an optical illusion created by our brains trying to make sense of the constantly changing display. The aurora exists as a three-dimensional phenomenon stretching across hundreds of miles of sky, but we perceive it as a flat curtain. As different parts of this vast display brighten and fade, our minds interpret the changes as flowing movement. This illusion of movement adds to the aurora's mesmerizing quality. Observers often report feeling hypnotized by the lights, unable to look away as they shift and pulse overhead. Time seems to slow down during aurora displays, minutes stretching into hours as viewers lose themselves in the cosmic performance. The northern lights have a southern twin called the aurora australis. While the northern lights capture most of our attention and imagination, identical phenomena occur around the South Pole. The aurora australis, or southern lights, forms from the same process as its northern counterpart, created when solar particles interact with Earth's magnetic field near the southern magnetic pole. The southern lights are less well known simply because fewer people live in the southern polar regions where they're visible. Antarctica, southern Chile, southern Argentina, and the southern tips of Australia and New Zealand occasionally witness these southern auroras. When viewed from space, both auroral ovals appear as mirror images of each other, synchronized dancers performing the same routine on opposite sides of our planet. Astronauts aboard the International Space Station have a unique perspective on both aurora displays, sometimes seeing the northern and southern lights simultaneously as they orbit above the polar regions from their vantage point. The aurora appears as a glowing ring around each pole, a cosmic crown adorning our planet. The intensity of northern lights follows an 11-year cycle. The sun's magnetic field reverses every 11 years, creating a cycle of solar activity that directly affects aurora displays on Earth. During solar maximum, when the sun is most active, solar flares and coronal mass ejections occur more frequently, creating more opportunities for strong aurora displays. During solar minimum, the sun is quieter, producing fewer particles and weaker magnetic disturbances. Aurora activity decreases during these periods, though the lights never disappear completely. Even during the quietest solar periods, the constant solar wind ensures that some aurora activity continues around the polar regions. This 11-year cycle means aurora viewing has its seasons on a cosmic scale. Amateur aurora photographers and northern lights enthusiasts learn to track solar activity, planning trips and expeditions around predicted peaks in the solar cycle. But even during quiet periods, the aurora maintains its gentle presence, a reminder of the constant connection between Earth and its star-indigenous peoples developed sophisticated methods for predicting aurora displays. Long before modern magnetometers and solar wind monitors, Arctic peoples learned to read subtle signs that preceded strong aurora activity. Some noticed changes in animal behavior, with caribou and other wildlife becoming restless before major displays. Others observed patterns in weather, ice formation, or the behavior of the aurora itself on previous nights. The Inuit developed a rich vocabulary for describing different types of aurora displays, with specific words for the various shapes, colors and intensities they observed over generations of watching the polar skies. This traditional knowledge represents thousands of years of careful observation and pattern recognition. While modern science has revealed the mechanisms behind the aurora, it hasn't diminished the value of indigenous understanding, which captures subtleties and relationships that instruments might miss. The northern lights appear different to cameras than to human eyes. Photographs of the aurora often show vivid greens, purples, and reds that seem almost artificially bright. While these colors exist in the aurora, the human eye perceives them differently than camera sensors do. Our eyes are less sensitive to certain wavelengths of light, particularly the red emissions that cameras capture easily. Most people see the northern lights as primarily green or white, with occasional hints of other colors during very active displays. The dancing curtains often appear as moving gray-green shapes with a subtle luminescence that's clearly distinct from starlight, but not as saturated as photographs suggest. This difference between perception and photography doesn't make either version less real or beautiful. The camera reveals colors and details invisible to our eyes, while human vision captures the dynamic movement and three-dimensional quality that still photographs cannot convey. Together, they provide a more complete understanding of this complex phenomenon. The aurora creates its own weather patterns in the upper atmosphere. The energy deposited by aurora particles heats the thin air in the thermosphere, causing it to expand and change its density. This heating can affect satellite orbits, radio communications, and even GPS accuracy during strong geomagnetic storms. The aurora also generates its own winds in the upper atmosphere, creating circulation patterns that exist nowhere else on Earth. These auroral winds can reach speeds of several hundred miles per hour, though they have no effect on surface weather due to the extreme altitude and thinness of the air. These upper atmospheric effects remind us that the aurora is not just a light show, but a complex interaction between solar energy and Earth's atmosphere. Every display represents a massive transfer of energy from space to our planet, quietly shaping the invisible layers of air that protect us from the harsh environment of space northern lights. Photography requires patience and preparation. Capturing the aurora on camera has become a popular pursuit, drawing photographers to remote locations across Alaska, northern Canada, Scandinavia, and Iceland. The best aurora photographs result from careful planning, understanding both the technical aspects of night photography and the natural patterns of aurora activity. Successful aurora photographers learn to read space weather forecasts, track in solar wind conditions and geomagnetic activity predictions. They scout locations during daylight, looking for compositions that will work in darkness. They dress for hours of standing in sub-zero temperatures, often in remote locations far from shelter or warmth. But perhaps most importantly, they develop patience. The aurora operates on its own schedule, sometimes appearing for just a few minutes, other times dancing for hours. Many photographers describe meditation-like states during long aurora vigils, finding peace in the quiet darkness while waiting for the lights to appear. The northern lights affect radio communications in subtle ways. The same charged particles that create the beautiful light displays also interact with radio signals traveling through the atmosphere. During aurora activity, radio communications can experience both enhancements and disruptions, depending on the frequency and the specific conditions in the ionosphere. Ham radio operators often welcome mild aurora activity because it can create unusual propagation paths, allowing communications over distances that would normally be impossible. The aurora acts like a natural radio reflector in the sky, bouncing signals in unexpected directions. However, strong geomagnetic storms that produce intense aurora displays can severely disrupt radio communications, GPS systems, and even power grids. These effects remind us that the aurora is part of a larger system of space weather that has real impacts on our modern technological society. Human settlements in aurora zones adapt their rhythms to the lights. Communities in northern Alaska, northern Canada, and Scandinavia live with the aurora as a regular part of their environment. Children grow up seeing the lights dance overhead, developing a casual familiarity with a phenomenon that visitors travel thousands of miles to witness. These communities often organize their winter activities around aurora seasons. Schools might schedule special outdoor classes during active periods. Tour guides develop expertise in reading the subtle signs that predict strong displays. Local photographers build careers around capturing their neighborhood lights for visitors from around the world. Living with the aurora creates a different relationship with the night sky. Rather than being an exotic phenomenon, the lights become part of the natural rhythm of seasons, weather, and cosmic activity. This familiarity doesn't breed contempt, but rather a deeper appreciation for the subtle variations and rare, spectacular displays that reward careful observation. The northern lights continue to reveal new secrets to scientists. Despite centuries of study and modern understanding of the underlying physics, the aurora still surprises researchers with unexpected behaviors and previously unknown phenomena. Recent discoveries include new types of aurora with names like STEVE, the picket fence aurora, and dunes. These discoveries often come from citizen scientists and amateur photographers who notice unusual features in their images and share them with researchers. The combination of improved camera technology and the passion of aurora enthusiasts has accelerated the pace of discovery, revealing details invisible to earlier generations of scientists. Each new type of aurora provides clues about the complex interactions between solar particles, Earth's magnetic field, and our atmosphere. The aurora serves as a natural laboratory for studying plasma physics, magnetism, and atmospheric science, with implications that extend far beyond Earth to understanding similar phenomena throughout the universe. The aurora appears in many shapes that have been given poetic names by those who study them. Curtains are the most common form, vertical sheets of light that seem to hang from the sky like luminous fabric swaying in an invisible breeze. These curtains can stretch for hundreds of miles across the horizon, their lower edges often appearing perfectly straight, while their upper portions fold and ripple with graceful irregularity. Arcs form when the aurora appears as smooth, continuous bands stretching across the sky. These arcs can persist for hours with little movement, creating a stable bridge of light from one horizon to another. Corona displays occur when the aurora appears directly overhead, with rays of light seeming to converge at a central point. like the spokes of a celestial wheel or the petals of a flower made from starlight. Rays shoot upward from the horizon like searchlight beams, sometimes flickering rapidly, other times holding steady for minutes at a time. Spirals and loops occasionally form during very active displays, creating shapes that seem almost too perfect to be natural. Each form has its own character and behavior, contributing to the aurora's reputation as nature's most dynamic art installation. The magnetic field lines that guide the aurora extend far into space. Earth's magnetosphere, the region dominated by our planet's magnetic field, stretches tens of thousands of miles into space on the day side and forms a long tail on the night side that extends well beyond the moon's orbit. The aurora represents the visible portion of interactions occurring throughout this vast magnetic domain. Solar particles spiral along these magnetic field lines, like beads sliding along invisible wires. The field lines act as highways, channeling particles from distant regions of space down into our atmosphere at specific locations. This is why the aurora appears in oval patterns around the magnetic poles, rather than randomly across the sky. When magnetic field lines from the sun connect with Earth's field lines through a process called reconnection, enormous amounts of energy transfer from the solar wind to our magnetosphere. This energy eventually finds its way into the atmosphere through the aurora, creating the brightest and most active displays. The entire process represents a delicate balance between solar forces trying to penetrate Earth's magnetic defenses and our planet's field, protecting us from the full intensity of solar radiation. Seasons affect when and where the northern lights appear most frequently. The aurora occurs year-round, but viewing conditions change dramatically with the seasons. In the Arctic summer, continuous daylight makes aurora observation impossible despite ongoing activity in the magnetosphere. The lights continue to dance overhead, invisible against the bright sky. Autumn and spring equinoxes mark peak aurora seasons because of the way Earth's magnetic field interacts with the solar wind. During these periods, the orientation of our planet's magnetic field relative to the sun's magnetic field creates more opportunities for the magnetic reconnection events that trigger strong displays. Winter provides the longest viewing windows with its extended darkness, but harsh weather often interferes with observation. Spring offers a perfect balance of reasonable weather and frequent activity. Many experienced aurora watchers plan their expeditions for March and April, when the combination of solar activity and viewing conditions reaches an optimal balance. The northern lights have inspired countless works of art, music, and literature. Painters have struggled for centuries to capture the aurora's ephemeral beauty on canvas. The challenge lies not just in reproducing the colors, which photographs now accomplish easily, but in conveying the sense of movement, scale, and emotional impact that the lights create in person. Classical composers have written symphonies attempting to translate the aurora's visual rhythms into musical form. The lights seem to dance to their own silent music, inspiring pieces that range from gentle flowing melodies to dramatic crescendos that mirror the sudden brightening of an active display. Writers and poets find the aurora endlessly inspiring, using it as a metaphor for everything from spiritual transcendence to the boundary between the known and unknown. The lights appear in creation myths, love stories, and tales of adventure in the far north. Each artistic interpretation adds another layer to humanity's relationship with this natural phenomenon. Different latitudes experience the aurora in unique ways. The northernmost communities, those lying directly beneath the auroral oval, see the lights frequently but often as a gentle glow on the northern horizon, rather than the dramatic overhead displays that occur slightly farther south. These frequent, subtle displays become part of the ambient light of winter nights. Communities at the southern edge of the aurora zone experience fewer displays, but when the lights do appear, they often manifest as spectacular overhead shows during geomagnetic storms. These rare but intense displays create lasting memories for viewers who might see the aurora only a few times in their lives. The latitude effect means that aurora tourism concentrates in a relatively narrow band around the globe. Cities like Fairbanks, Yellowknife, Tromsø, and Rovaniemi have built entire industries around providing visitors access to optimal aurora viewing conditions. Each location offers its own advantages in terms of weather patterns, infrastructure, and surrounding landscapes. Modern technology has transformed how we predict and study the aurora. Satellites positioned between Earth and the Sun monitor solar wind conditions, providing advance warning of incoming disturbances that might trigger aurora displays. Ground-based magnetometers scattered across the polar regions measure the strength and direction of magnetic field changes associated with aurora activity. Computer models now attempt to predict aurora intensity and location with increasing accuracy. Though the chaotic nature of space weather still makes precise forecasting, challenging aurora forecasts typically provide probability estimates rather than definitive predictions. Acknowledging the complex interactions that determine when and where the lights will appear, smartphone apps deliver aurora alerts to enthusiasts around the world, creating a global community of aurora watchers connected by their shared passion. Social media fills with aurora photographs during active periods, allowing people far from the polar regions to share in the experience of those lucky enough to witness displays firsthand. The aurora creates a unique form of natural meditation for many observers. Standing beneath the dancing lights often produces a profound sense of calm and connection with something larger than oneself. The combination of the vast scale, the gentle movement, and the pristine silence of aurora viewing locations creates conditions naturally conducive to contemplative states. Many people describe losing track of time during aurora displays, becoming so absorbed in watching the lights that hours pass unnoticed. This timeless quality reflects both the hypnotic nature of the aurora's movement and the way extraordinary experiences can shift our perception of temporal flow. Aurora viewing often becomes a form of active meditation, requiring patience, presence, and acceptance of natural rhythms beyond human control. Observers learn to dress warmly, find comfortable positions, and simply wait with open awareness for whatever the sky might offer. This practice of patient observation transfers to other aspects of life, teaching lessons about being present in the moment. The chemistry of aurora colors reveals the composition of our upper atmosphere. Each color corresponds to specific atoms or molecules being excited by incoming solar particles. The dominant green comes from oxygen atoms about 60 miles above the surface. In a region where oxygen exists as individual atoms, rather than the paired molecules we breathe, the red aurora, usually too faint for human eyes to detect, comes from oxygen atoms much higher in the atmosphere, around 150 to 300 miles up. At these altitudes, the air is so thin that excited oxygen atoms can hold their energy for much longer before releasing it as red light. Blue and purple hues indicate interactions with nitrogen molecules at lower altitudes. These colors often appear at the bottom edge of aurora displays, where the atmosphere becomes dense enough for nitrogen to dominate. The entire spectrum of aurora colors maps out the layered structure of Earth's upper atmosphere in real time. Spacecraft and astronauts experience the aurora from unique perspectives. Satellites orbiting within the aurora zone sometimes pass directly through the energetic particle streams that create the lights, measuring the intensity and composition of the solar wind as it interacts with Earth's magnetic field. Astronauts aboard the International Space Station orbit at an altitude of about 250 miles, placing them sometimes above and sometimes within the aurora displays. From their perspective, the aurora appears as a glowing ring around each pole, occasionally bright enough to illuminate the space station and the Earth's surface below. These space-based observations provide data impossible to obtain from the ground, revealing details about aurora formation, energy transfer, and the three-dimensional structure of displays. The combination of ground-based observation and space-based measurement has dramatically improved our understanding of aurora physics over the past few decades. The aurora influences animal behavior in ways scientists are still discovering. Caribou migrations sometimes seem to correlate with periods of high aurora activity, though whether this represents a direct response to the lights or to associated changes in magnetic fields remains unclear. Some birds show altered migration patterns during intense geomagnetic storms that produce strong aurora displays. Domestic animals in aurora zones occasionally display unusual behavior during active periods. Dogs might howl at the lights or become restless during displays. Horses and cattle sometimes gather together or show signs of agitation when the aurora is particularly bright or active. These behavioral changes might result from the animals detecting magnetic field fluctuations associated with aurora activity, or they might simply respond to the unusual lighting conditions. Many animals navigate using magnetic cues, so the magnetic disturbances that create the aurora could potentially affect their sensory systems in subtle ways. Aurora photography has evolved into a sophisticated art form requiring specialized techniques and equipment. Modern cameras can capture colors and details invisible to the human eye. But successful aurora photography demands understanding both the technical aspects of low-light imaging and the natural patterns of aurora behavior. Long exposures reveal the aurora's structure and color palette, but they also smooth out the rapid movements that make the lights so captivating to observe directly. Some photographers use multiple short exposures, combined into time-lapse sequences, to better capture the aurora's dynamic nature. The challenge for aurora photographers lies in balancing technical precision with artistic vision. Equipment must function reliably in extreme cold, while the photographer remains alert and creative during long hours of waiting in darkness. Many describe aurora photography as a form of meditation that combines technical skill with patient observation of natural rhythms. Local legends about the aurora vary dramatically across different cultures and regions. Some Siberian peoples believed the aurora represented the spirits of hunters who had died violent deaths, forever pursuing their prey across the sky. Scandinavian folklore sometimes portrayed the lights as reflections from schools of herring swimming through celestial waters. Native American tribes developed their own rich traditions around the aurora. Some saw the lights as fires built by spirits to warm the souls of those who had passed away. Others interpreted different aurora colors as messages from ancestors or omens of future events. These diverse cultural interpretations reflect humanity's deep need to find meaning and story in natural phenomena. While modern science has revealed the physical mechanisms behind the aurora, these ancient stories continue to resonate because they capture the emotional and spiritual impact of witnessing something so beautiful and mysterious. The aurora serves as a natural laboratory for studying plasma physics. The interactions between charged particles and magnetic fields that create the aurora occur throughout the universe, from the magnetospheres of other planets to the vast spaces between stars. Understanding aurora formation helps scientists interpret similar phenomena observed around Jupiter, Saturn, and other magnetized planets. Solar wind interactions with planetary magnetic fields create aurora-like displays throughout the solar system. Jupiter's aurora, powered by particles from its volcanic moon Io, creates displays far more intense than anything seen on Earth. Saturn's aurora appears primarily in ultraviolet wavelengths, invisible to human eyes, but detectable by specialized instruments. These comparisons help scientists understand how magnetic fields, atmospheres, and stellar radiation interact across different environments. The aurora represents a fundamental process in plasma physics that scales from planetary to galactic dimensions, making Earth's displays a window into cosmic phenomena occurring throughout the universe. Climate change affects aurora viewing conditions in subtle but measurable ways. Changing weather patterns in the Arctic alter cloud cover statistics, potentially affecting how often clear skies coincide with aurora activity. Shift in a storm tracks might change the frequency of clear nights at popular aurora viewing locations. More significantly, changes in Earth's upper atmosphere due to increasing greenhouse gas concentrations might affect aurora formation and appearance. The thermosphere, where most aurora activity occurs, is actually cooling as lower atmospheric layers warm, potentially changing how solar particles interact with atmospheric gases. These effects remain relatively minor compared to natural variations in solar activity and Earth's magnetic field. But they remind us that even phenomena occurring hundreds of miles above the surface connect to changes happening at ground level. The aurora exists as part of a complex system linking solar activity, Earth's magnetic field, atmospheric chemistry, and ultimately, climate patterns. Human settlements in the far north develop unique relationships with aurora seasons. Communities above the Arctic Circle experience months of continuous darkness during winter, making them ideally positioned for aurora observation, but also creating challenges for daily life. The aurora becomes part of the rhythm of polar night, providing natural illumination and a connection to cosmic forces during the darkest months. Children growing up in these communities often take the aurora for granted, the same way children in temperate climates might regard rainbows or snow schools, incorporate aurora science into their curricula, teaching students about the connections between their local skies and solar physics. Local artists and craftspeople draw inspiration from the lights, creating works that interpret aurora patterns in traditional and contemporary forms. These communities serve as guardians of aurora knowledge, maintaining observational traditions that span generations while adapting to modern understanding and technology. Their perspective on the aurora combines intimate familiarity with deep respect for a phenomenon that visitors travel thousands of miles to witness. The northern lights dance to rhythms older than human memory. Each display follows patterns that connect to cycles within cycles, from the 11-year solar maximum to the daily rotation of our planet beneath the auroral oval. But there are subtler rhythms too, ones that reveal themselves only to those who watch the skies across many seasons and years. Solar particles don't arrive at Earth in a steady stream, but in waves and pulses that reflect the complex magnetic dynamics of our star. When solar wind speed increases, the aurora often brightens and becomes more active. When the magnetic field carried by the solar wind aligns in certain ways with Earth's field, the lights can suddenly explode across the sky in what scientists call substorms. These substorms follow their own mysterious timing. They might occur every few hours during active periods, or remain quiet for days despite favorable solar conditions. The aurora seems to store energy gradually, then release it in brilliant bursts that can transform a quiet green arc into a writhing curtain of light spanning the entire sky. Experienced aurora watchers learn to read these rhythms, recognizing the subtle signs that precede major displays. A slight brightening along the northern horizon might signal the beginning of activity. A gentle pulsing in the lights often indicates that more dramatic changes lie ahead. The aurora teaches patience to those who would understand its ways. The magnetic field lines that channel the aurora stretch and twist like invisible elastic bands. When solar wind pressure increases, these field lines compress on the day side of Earth and stretch longer on the night side. Eventually, they snap back like rubber bands, accelerating particles earthward and triggering the sudden brightenings that make aurora displays so unpredictable and exciting. This process, called magnetic reconnection, occurs constantly but irregularly in Earth's magnetotail. Each reconnection event sends a burst of energy toward the polar regions, where it manifests as increased aurora activity. The delay between the reconnection and the visible aurora can range from minutes to hours, adding another layer of complexity to aurora prediction. Scientists monitor this process using networks of ground-based magnetometers and spacecraft positioned throughout Earth's magnetosphere. The data reveals a dynamic system in constant motion, with energy flowing from the solar wind through magnetic field lines to the upper atmosphere, where it finally becomes visible as the northern lights. Aurora displays create their own electromagnetic signatures that affect the environment in ways both subtle and profound. The electrical currents associated with active aurora can induce voltages in long conductors like power lines, pipelines, and railway tracks. During extreme events, these induced currents can cause power outages, pipeline corrosion, and navigation errors. But most of the time, these effects remain invisible to daily life. The aurora represents a gentle transfer of energy from space to Earth, a cosmic gift that arrives as beauty rather than disruption. The same electromagnetic processes that occasionally challenge our technology also create one of nature's most spectacular displays. Radio enthusiasts have long known that aurora activity can create unusual propagation conditions for certain frequencies. The ionized particles that produce the lights also reflect radio signals, sometimes allowing communication over impossible distances. Amateur radio operators often monitor aurora forecasts, not for the visual display, but for the unique communication opportunities they create. These radio effects provide another way to detect aurora activity, even during daylight hours when the lights remain invisible. Radio reflections from the aurora have a distinctive sound, described by operators as a musical tone that rises and falls with the intensity of the display. Through radio, the silent aurora finds its voice. The aurora appears different from various locations within its range, creating unique viewing experiences that depend on magnetic latitude and local geography. Communities directly beneath the auroral oval often see the lights as a gentle glow along the northern horizon, sometimes so subtle that only experienced observers notice the soft green luminescence among the stars. Locations slightly south of the oval's center experience more dramatic displays, with the aurora appearing higher in the sky and showing more dynamic movement. These regions offer the classic aurora experience, with curtains of light dancing directly overhead during active periods. Even farther south, the aurora appears only during significant geomagnetic storms, but these rare events often produce the most memorable displays. The lights appear as a strange glow on the northern horizon, sometimes accompanied by unusual colors and shapes unfamiliar to regular aurora watchers. These southern sightings often generate excitement and wonder among populations unaccustomed to seeing the phenomenon. Photographers have discovered that different geographic locations offer distinct advantages for aurora imaging. Coastal areas provide opportunities to capture the lights reflecting in water, creating mirror images that double the visual impact. Mountain regions allow photographers to frame the aurora against dramatic landscapes, adding terrestrial elements that provide scale and context. Each location develops its own photographic traditions and techniques adapted to local conditions. Icelandic photographers become experts at incorporating volcanic landscapes and thermal features. Scandinavian artists learn to use snow-covered forests and traditional architecture as foreground elements. Canadian photographers master the art of capturing the aurora over frozen lakes and tundra landscapes. The aurora influences local weather patterns in the upper atmosphere through processes that remain partially mysterious to scientists. The energy deposited by aurora particles heats the thin air of the thermosphere, causing it to expand and creating circulation patterns that exist nowhere else on Earth. These auroral winds can reach extreme speeds, but have no direct effect on surface weather due to the extreme altitude where they occur. However, Some researchers have proposed connections between space weather events that create strong aurora displays and changes in atmospheric circulation patterns that eventually influence surface weather. These connections remain speculative and controversial, representing one of the frontiers where aurora science intersects with meteorology and climate research. The heating effect of the aurora does have measurable consequences for satellites orbiting in the upper atmosphere. During active periods, atmospheric expansion increases drag on spacecraft, affecting their orbits and requiring occasional adjustments to maintain proper altitude. This represents one of the ways that space weather, visible through the aurora, impacts modern technology. Traditional aurora observation required nothing more than clear skies and patience, but modern enthusiasts have access to tools that enhance the experience in remarkable ways. Smartphone apps provide real-time aurora forecasts and alerts, allowing viewers to time their expeditions for optimal conditions. Digital cameras reveal colors and structures invisible to the naked eye, while time-lapse photography captures the aurora's movement in compressed time. But perhaps the most valuable tool remains the simplest: a comfortable chair or blanket that allows extended viewing in cold conditions. The aurora rewards patient observation, revealing its subtleties only to those willing to spend hours beneath the dancing lights. Quick glimpses rarely capture the full experience of watching an aurora display develop, peak, and fade over the course of a night. Many experienced aurora watchers develop personal rituals around viewing the lights. Some prefer solitary observation, finding that the aurora creates a meditative state best experienced alone. Others gather in small groups, sharing the wonder while maintaining the quiet reverence that the lights seem to inspire. The social aspect of aurora watching has evolved with modern communication technology. Online communities share real-time reports of activity, photographs, and viewing locations. Social media fills with aurora images during active periods, creating virtual gatherings of enthusiasts separated by thousands of miles, but united by their shared passion for the lights. These digital connections have democratized aurora knowledge, allowing experienced observers to share their expertise with newcomers and creating global networks of aurora watchers who monitor conditions and share observations across time zones and continents. The aurora serves as a gateway to understanding our planet's place in the solar system and the complex relationships between Earth and space. Every display represents a moment when cosmic forces become visible and tangible, bridging the gap between the abstract concepts of space physics and direct sensory experience. Children who grow up seeing the aurora often develop intuitive understanding of concepts like magnetic fields, solar wind, and atmospheric chemistry long before they encounter these topics in formal education. The lights provide concrete examples of invisible forces and processes that might otherwise remain purely theoretical. This educational value extends beyond science to philosophy and spirituality. The aurora confronts viewers with the reality of forces and scales beyond human control or comprehension. Standing beneath the dancing lights often produces profound feelings of connection to something larger than individual existence. Many cultures have incorporated this transformative aspect of aurora viewing into spiritual practices and coming-of-age ceremonies. The lights serve as a natural cathedral, a sacred space where the boundary between earth and sky dissolves into flowing curtains of colored light. The timing of aurora displays follows patterns that reflect both solar activity and Earth's position in its orbit around the Sun. The equinoxes mark peak aurora seasons because of geometric relationships between Earth's magnetic field and the solar wind that create optimal conditions for magnetic reconnection events. But within these broad seasonal patterns lie subtler rhythms related to the 27-day rotation of the Sun and the way solar wind streams interact with Earth's magnetosphere. Experienced aurora watchers learn to recognize these patterns, planning their viewing expeditions around predicted peaks in activity. The unpredictability that remains after accounting for all known patterns adds to the aurora's appeal. Even with sophisticated forecasting tools and deep understanding of the underlying physics, the aurora retains an element of mystery and surprise that keeps enthusiasts returning to the polar skies season after season. This combination of pattern and chaos reflects the complex nature of the solar terrestrial system itself. The aurora emerges from the intersection of multiple cycles and processes, each operating on different timescales and influencing the others in ways that create both predictable trends and sudden surprises. The aurora creates unique challenges and opportunities for different forms of artistic expression. Painters struggle to capture the aurora's movement and ethereal quality in static media, leading to abstract interpretations that emphasize the emotional impact rather than literal representation. The most successful aurora paintings often focus on the interplay between light and landscape, using the aurora to transform familiar scenes into otherworldly visions. Musicians find inspiration in the aurora's rhythmic pulsations and flowing movements, composing pieces that translate visual rhythms into auditory experience. The challenge lies in capturing the aurora's scale and grandeur while maintaining the intimacy and wonder that individual observers experience beneath the lights. Writers and poets use the aurora as metaphor and setting, drawing on its associations with mystery, beauty, and the boundary between known and unknown. The lights appear in literature as symbols of transcendence, natural power, and the persistent human desire to find meaning in natural phenomena. Each artistic interpretation adds layers to the cultural significance of the aurora, ensuring that future generations will inherit not just scientific understanding, but also rich traditions of creative response to one of nature's most inspiring displays. The study of aurora has contributed to fundamental advances in plasma physics, magnetospheric science, and our understanding of how charged particles behave in magnetic fields. These advances have applications far beyond Earth, helping scientists interpret observations of similar phenomena around other planets and in distant astrophysical environments. Jupiter's aurora, powered by particles from its volcanic moon Io, creates displays far more intense than anything seen on Earth. Saturn's aurora appears primarily in ultraviolet wavelengths and shows complex relationships to the planet's unique magnetic field structure and ring system. Even planets without significant atmospheres can show aurora-like phenomena where solar wind interacts directly with surface materials. These comparative studies reveal universal principles governing how stellar winds interact with planetary magnetic fields throughout the cosmos. The aurora serves as a natural laboratory for studying processes that occur on scales from planetary to galactic, making every display a window into cosmic physics. The northern lights continue to evolve as our sun ages and Earth's magnetic field changes over geological time. The sun's output varies not just on 11-year cycles, but also on much longer time scales that affect the intensity and frequency of aurora displays over centuries and millennia. Earth's magnetic field itself changes over time, with the magnetic poles wandering and the field strength fluctuating in ways that alter where and how often the aurora appears. These slow changes ensure that the aurora of the future will differ subtly from the displays we see today. Even as the underlying physics remains constant, climate change in the upper atmosphere might also influence aurora formation and appearance in ways scientists are only beginning to understand. The complex relationships between atmospheric chemistry, temperature, and aurora formation represent active areas of research that will likely yield new insights in coming years. These long-term perspectives remind us that the aurora we see today represents just one moment in a much longer story of solar evolution, planetary magnetism, and atmospheric change. Every display connects us not just to current space weather, but to the deep history and future of our solar system. The aurora remains one of the few natural phenomena that can still inspire genuine wonder in our technology-saturated world. In an age when most mysteries have been explained and most frontiers explored, the aurora continues to surprise and delight observers with its beauty, complexity, and subtle variations that reward careful attention. This enduring capacity for wonder reflects both the aurora's objective magnificence and its deeper significance as a visible connection between Earth and cosmos. Standing beneath the northern lights, observers experience directly the reality that our planet exists within the sun's sphere of influence. Connected by invisible threads of magnetism and solar wind to the star that powers all life on Earth, the aurora teaches lessons about patience, observation, and acceptance of natural rhythms beyond human control. It rewards those who venture into cold and darkness with displays of beauty that no artificial creation can match. In our increasingly indoor artificial world, the aurora calls us back to direct engagement with natural forces and cosmic cycles. As you drift toward sleep tonight, perhaps you'll carry with you some sense of the quiet majesty that dances across polar skies. The aurora continues its ancient rhythm, painting the darkness with light, connecting Earth to sun, and reminding us that we live within a universe far more beautiful and mysterious than our daily lives usually reveal. The northern lights flow on through the night, gentle and eternal, a cosmic lullaby written in luminous curtains across the star-filled sky. In their silent dance lies a peace that transcends understanding, a beauty that needs no explanation, a wonder that asks only to be witnessed with grateful eyes. The aurora appears in cycles within cycles, following rhythms that stretch across time, scales both vast and intimate. Solar rotation creates 27-day patterns as active regions on the sun's surface sweep past Earth, sometimes sending streams of faster solar wind that trigger recurring aurora displays. These high-speed streams can persist for months, creating windows of increased activity that experienced observers learn to anticipate. Within these longer patterns lie shorter cycles tied to Earth's daily rotation. The aurora oval rotates with the planet, bringing different longitudes beneath the lights as night progresses. This means that aurora activity often peaks at specific local times, typically between 10 in the evening and 2 in the morning, when magnetic conditions favor the most dynamic displays. The moon's phases also influence aurora viewing, though not through any direct physical effect. Instead, the lunar cycle affects viewing conditions, as moonlight can either illuminate the landscape beautifully or wash out fainter aurora displays. Many photographers prefer the dark skies around new moon for capturing the most subtle colors and structures, while others appreciate how full moonlight creates dramatic silhouettes and reflections. These overlapping cycles create a complex rhythm that experienced aurora watchers learn to read like a natural calendar. The lights follow patterns within patterns, each display unique yet part of larger sequences that unfold over days, weeks, and years. This temporal complexity adds depth to aurora observation, rewarding those who track the lights across multiple seasons. The aurora influences the upper atmosphere in ways that cascade through layers of air hundreds of miles thick. When energetic particles collide with atmospheric gases, they don't just create light, they also heat the thin air of the thermosphere, causing it to expand and creating ripples that propagate downward through the atmosphere's layered structure. This heating effect can double the density of air at satellite altitudes during major geomagnetic storms. Spacecraft experience increased atmospheric drag that can alter their orbits significantly, requiring mission controllers to plan orbital adjustments around predicted space weather events. The International Space Station occasionally needs to boost its altitude to compensate for drag increases during intense aurora periods. The expansion of the upper atmosphere during aurora activity creates pressure waves that travel downward at the speed of sound, taking hours to reach the lower atmosphere. These waves are too subtle to affect surface weather directly, but they represent one of the many ways that space weather events ripple through Earth's entire atmospheric system. Some researchers study these atmospheric responses to better understand how energy from space couples with Earth's atmospheric dynamics. The aurora serves as a visible marker of energy transfer processes that affect the entire planet, even in regions far from where the lights appear. Traditional methods for predicting aurora activity relied on careful observation of patterns that often escaped formal scientific measurement. Indigenous peoples of the Arctic developed sophisticated understanding of the subtle signs that preceded major displays, reading clues in cloud formations, animal behavior, and the appearance of previous night's aurora. Sami reindeer herders noticed that their animals became restless before strong aurora displays, possibly responding to magnetic field fluctuations that humans couldn't detect directly. Inuit observers tracked relationships between weather patterns and aurora activity, developing prediction methods that sometimes proved more accurate than early scientific attempts. These traditional knowledge systems recognized connections that modern science has only recently begun to understand. The relationship between atmospheric pressure systems and geomagnetic activity, for example, involves complex interactions between solar wind pressure and Earth's magnetosphere that can influence both space weather and terrestrial weather patterns. Contemporary aurora forecasting combines traditional observational wisdom with satellite monitoring, computer modeling, and global networks of ground-based instruments. But the most experienced observers still rely partly on intuition developed through years of watching the lights, recognizing subtle signs that instruments might miss. The colors of the aurora shift and blend in combinations that depend on altitude, atmospheric composition, and the energy of incoming particles. Green remains the most common color because oxygen at 60 to 150 miles altitude emits this wavelength most efficiently when excited by typical solar wind particles. But during intense geomagnetic storms, higher energy particles can penetrate deeper into the atmosphere, exciting oxygen at lower altitudes where collisions occur more frequently. This creates the rare all-sky red aurora that appears during the most extreme space weather events, painting the entire sky in crimson light that can be visible even from mid-latitude locations. Blue and violet hues indicate interactions with nitrogen molecules, typically appearing at the lower edges of aurora displays, where the atmosphere becomes dense enough for nitrogen to dominate. These cooler colors often flicker rapidly, creating a shimmering effect that adds visual texture to the overall display. Purple combines red oxygen emissions with blue nitrogen light, creating complex color gradients that shift and flow as different atmospheric layers respond to varying particle energies. The entire spectrum tells a story of atmospheric composition and energy transfer, written in real time across the polar sky. Some aurora displays show colors that cameras capture more vividly than human eyes can perceive. Our vision evolved primarily for daylight conditions, making us less sensitive to certain wavelengths that aurora produces. Red emissions, in particular, often appear faint or invisible to direct observation while showing prominently in photographs. This difference between visual and photographic aurora experiences has created some confusion among first-time observers who expect to see the vivid colors they've seen in images. The human eye typically perceives aurora as primarily green or white, with occasional hints of other colors during very active displays. Long exposure photography reveals the aurora's full color palette by accumulating light over time, allowing faint emissions to build up to visible levels. But photographs cannot capture the dynamic movement and three-dimensional quality that make direct observation so compelling. Many experienced aurora watchers prefer the subtle beauty of visual observation, finding that the aurora's gentle luminescence and flowing movement create a meditative experience that photographs, despite their technical superiority, cannot fully convey. The aurora creates its own unique lighting conditions that affect photography, wildlife behavior, and human perception in subtle ways. Unlike artificial lighting, aurora illumination changes constantly in intensity, color, and direction, creating challenges for any activity that depends on consistent lighting. Photographers working beneath active aurora displays must constantly adjust their camera settings to account for changing light conditions. A bright corona display might require exposure times of just a few seconds, while faint arcs need minutes of exposure to appear clearly in images. Wildlife in aurora zones has adapted to these changing natural lighting conditions over evolutionary timescales. Some Arctic animals show behavioral changes during bright aurora displays, possibly responding to the unusual lighting or to associated magnetic field fluctuations that affect their navigation systems. Human settlements in aurora regions often notice how bright displays can create false dawn conditions, with residents sometimes waken early during intense events. The aurora provides enough illumination to read by during major displays, creating natural lighting conditions that exist nowhere else on Earth. The electromagnetic effects associated with aurora activity extend far beyond the visible light display. The same particle interactions that create the beautiful colors also generate radio waves, magnetic field fluctuations, and electrical currents that can be detected by sensitive instruments around the world. Ground-based magnetometers record the magnetic signatures of aurora activity as characteristic patterns of magnetic field variations. These measurements provide early warning of geomagnetic storms and help scientists understand the global extent of aurora-related phenomena. Radio telescopes detect natural radio emissions generated by aurora processes, revealing details about particle energies and magnetic field structures that optical observations cannot provide. These radio aurora can occur even during daylight, when the visual aurora remains invisible. The electrical currents associated with aurora displays flow through the upper atmosphere in patterns that mirror the visible aurora forms. These currents can induce voltages in ground-based conductors, creating the technological impacts that make space weather a practical concern for modern society. Aurora research has contributed to fundamental advances in plasma physics that have applications throughout science and technology. The natural laboratory provided by aurora displays has helped scientists understand how charged particles behave in magnetic fields under conditions impossible to recreate in terrestrial laboratories. These insights have informed the development of fusion energy research, where similar plasma physics principles apply to containing and controlling hot, ionized gases. The magnetic confinement techniques used in experimental fusion reactors draw partly on understanding gained from studying aurora formation processes. Space weather prediction, crucial for protecting satellites and astronauts, relies heavily on knowledge gained from aurora research. The same processes that create beautiful light displays can also damage spacecraft electronics and pose radiation hazards to humans in space. Magnetospheric physics, developed largely through aurora studies, now helps scientists understand similar phenomena around other planets and stars. The aurora serves as a window into universal processes that occur wherever stellar winds interact with planetary magnetic fields. The aurora appears in historical records dating back thousands of years, providing a unique long-term data set for studying space weather and solar activity cycles. Ancient Chinese astronomers recorded aurora observations as early as 2,000 years ago, describing them as dragons dancing in the northern sky. Medieval European chronicles contain detailed descriptions of rare aurora displays that appeared during periods of intense solar activity. The Great Aurora of 1770 was visible across Europe and North America, bright enough to cause widespread alarm among populations unfamiliar with the phenomenon. These historical records help scientists understand long-term patterns in solar activity and geomagnetic disturbances that extend far beyond the period of modern scientific observation. The aurora serves as a natural recorder of space weather events spanning millennia. Combining historical aurora records with other indicators of past solar activity, such as tree ring data and ice core measurements, scientists can reconstruct the history of solar variability and its effects on Earth's climate and magnetic field over thousands of years. The cultural impact of aurora observations extends beyond folklore into the development of early astronomy and natural philosophy. Many Arctic cultures developed sophisticated understanding of celestial mechanics, partly through careful observation of aurora patterns and their relationships to seasonal cycles. The aurora's connection to magnetic phenomena was recognized long before the underlying physics was understood. Compass variations during aurora displays provided early evidence for relationships between terrestrial magnetism and celestial events. Early scientific expeditions to the Arctic often included aurora observation as a primary objective, contributing to the development of geophysics and atmospheric science. These expeditions established the first systematic aurora monitoring stations and began the quantitative study of aurora phenomena. The International Polar Years, beginning in the late 19th century, coordinated global aurora observations that revealed the worldwide extent of geomagnetic disturbances and established aurora research as an international scientific collaboration. Modern aurora tourism has created economic opportunities for remote northern communities while raising awareness of space weather and atmospheric science among the general public. Cities like Fairbanks, Yellowknife, and Tromsø have built significant tourism industries around aurora viewing, providing infrastructure and services for visitors from around the world. These tourism operations often employ local guides who combine traditional knowledge of aurora patterns with modern forecasting techniques, creating unique educational experiences that bridge indigenous wisdom and contemporary science. Aurora tourism also supports local artists, craftspeople, and photographers who draw inspiration from the lights. The economic impact extends beyond direct tourism services to include aurora-themed art, jewelry, and other cultural products that carry the aurora's influence far from its northern origins. The growth of aurora tourism has created a global community of aurora enthusiasts who share observations, photographs, and experiences through online platforms and social networks. This community contributes to citizen science efforts and helps researchers understand aurora phenomena from multiple perspectives. The aurora connects Earth to the broader cosmic environment in ways that become more apparent as space exploration expands our perspective beyond our home planet. Every aurora display represents a moment when interplanetary space weather becomes visible and tangible, bridging the gap between Earth and the solar system. Spacecraft exploring the outer solar system encounter similar phenomena around other magnetized planets, providing comparative data that enhances our understanding of aurora formation processes. The Juno mission to Jupiter has revealed aurora displays thousands of times more intense than Earth's, powered by the planet's powerful magnetic field and volcanic moon. Io future missions to explore the magnetospheres of ice moons like Europa and Enceladus may discover aurora-like phenomena that could provide clues about subsurface oceans and potential habitability. The aurora serves as a universal signature of magnetic field interactions that occur throughout the cosmos. As human presence in space expands, understanding space weather and its effects becomes increasingly important for protecting astronauts and spacecraft. The aurora provides a beautiful reminder of the radiation environment that surrounds Earth and the magnetic field that shields us from its full intensity. The aurora teaches lessons about time, patience, and the rewards of careful observation that extend far beyond aurora watching itself. Successful aurora observation requires accepting natural rhythms beyond human control, developing patience for events that cannot be rushed, and finding contentment in witnessing rather than controlling natural phenomena. These lessons transfer to other aspects of life and other forms of nature observation. The skills developed through aurora watching, patience, careful observation, and acceptance of uncertainty apply to bird watching, astronomy, weather observation, and many other activities that connect us with natural cycles and processes. The aurora also demonstrates the value of being present in the moment, rather than focusing entirely on capturing or documenting experiences. While photography can preserve aurora memories, the most profound aurora experiences often occur during moments of simple witnessing without distraction. Many aurora watchers develop a contemplative relationship with the lights that enriches their overall connection to natural phenomena and seasonal cycles. The aurora becomes a teacher, offering lessons about beauty, impermanence, and the rewards of patient attention to the world around us. The scientific study of aurora continues to reveal new phenomena and deepen our understanding of magnetospheric processes. Recent discoveries include previously unknown types of aurora, with names like STEVE, picket fence aurora, and dunes, each representing different physical processes or observational perspectives. These discoveries often result from collaboration between citizen scientists and professional researchers, with amateur photographers and aurora enthusiasts providing observations and images that lead to scientific breakthroughs. The combination of improved camera technology and passionate observation has accelerated the pace of aurora discovery. Artificial intelligence and machine learning techniques are now being applied to analyze vast databases of aurora images and magnetometer data, revealing patterns and relationships that human researchers might miss. These computational approaches complement traditional observational methods and theoretical modeling. Space-based aurora observations from satellites and the International Space Station provide perspectives impossible to achieve from the ground, revealing the three-dimensional structure of aurora displays and their connections to magnetospheric processes occurring thousands of miles above Earth's surface. The aurora serves as a bridge between the visible and invisible aspects of our planet's relationship with space. While we can see the beautiful light displays with our own eyes, they represent just the visible portion of complex electromagnetic interactions occurring throughout Earth's magnetosphere. Understanding these invisible processes helps us appreciate the aurora's true significance as more than just a pretty light show. Each display represents a moment when cosmic forces become accessible to human perception, offering direct sensory experience of phenomena that usually remain beyond our awareness. The aurora reminds us that Earth exists within the sun's extended atmosphere, connected by invisible threads of magnetic force and flowing particles to the star that powers all life on our planet. We live within a dynamic system that extends far beyond Earth's surface into the solar wind and interplanetary space. This cosmic perspective, revealed through aurora observation, enriches our understanding of Earth's place in the solar system and our connection to the broader universe. The aurora makes visible our planet's membership in a community of worlds all influenced by solar activity and space weather. As the night deepens and your thoughts begin to drift like the gentle aurora curtains themselves, perhaps you can sense the quiet dance that continues overhead, even when clouds hide the lights from view. The aurora flows on through Arctic darkness, painting the sky with colors that exist nowhere else in nature, following rhythms older than human memory. In remote cabins scattered across Alaska and northern Canada, in the forests of Scandinavia, and along the shores of Arctic seas, people pause their evening activities to step outside and look up at the dancing lights. Some see them every clear night during winter. Others witness them only a few times in their lives. But all who see the aurora carry something of its beauty with them, a memory of light that defies explanation and asks only to be appreciated. The aurora connects us across distance and time to all who have ever paused beneath the northern lights. Indigenous hunters following caribou migrations thousands of years ago, Viking explorers navigating by stars and aurora glow, modern scientists unlocking the secrets of magnetospheric physics, children in Arctic communities who grow up thinking the dancing lights are as natural as sunrise, visitors who travel thousands of miles for a glimpse of the cosmic ballet performed nightly above the polar regions. Tonight, as sleep draws near, the aurora continues its ancient rhythm. Solar particles stream across the void between Earth and Sun, following magnetic field lines that guide them toward the polar regions, where they'll paint the darkness with ethereal light. The process unfolds with the patient timing of cosmic clockwork, neither hurried nor delayed, following laws of physics that govern interactions between stars and planets throughout the universe. Somewhere above the clouds that might hide them from earthbound observers, the northern lights flow in curtains of green and silver, rose and violet, dancing to music only they can hear. They ask nothing of us, except perhaps a moment of wonder, a pause in our busy lives to look up and remember that we live within something far grander and more beautiful than our daily concerns usually reveal. The aurora reminds us that mystery and beauty persist in our world, that there are still phenomena that can inspire genuine awe despite our scientific understanding of their mechanisms. Knowledge of how the aurora forms doesn't diminish its magic, but rather adds layers of appreciation for the elegant physics that creates such beauty from the simple interaction of particles and magnetic fields. As your breathing slows and your body settles into rest, perhaps you'll dream of curtains of light flowing across star-filled skies. Maybe you'll imagine yourself standing in the Arctic silence, watching the cosmic dance that has inspired humanity since we first looked up at the night sky and wondered at the lights that painted the darkness with flowing color. the northern lights continue their eternal performance, indifferent to our observation, but somehow graced by our appreciation. They dance for no audience except perhaps the stars themselves, yet they offer their beauty freely to any who venture into the darkness with eyes open to wonder. In their silent flowing lies a peace that needs no explanation, a beauty that transcends understanding, a reminder that we live within a universe far more magnificent than we usually take time to notice. The aurora flows on through the night, gentle and eternal, a cosmic lullaby written in light across the infinite canvas of the polar sky. Sky. The aurora exists in a realm between Earth and space where the rules of both domains intersect in remarkable ways. This boundary region, called the magnetosphere, extends far beyond what we might consider Earth's atmosphere, reaching tens of thousands of miles into space on the sunward side and stretching even farther in the opposite direction. Like a cosmic teardrop trailing behind our planet as it orbits the sun. Within this vast magnetic cocoon, particles from the solar wind become trapped and guided along invisible highways of magnetic force. These particles can remain stored in the magnetosphere for days or even weeks, slowly drifting closer to Earth until they finally plunge into the upper atmosphere to create the lights we see. This storage and release mechanism helps explain why aurora activity doesn't always correspond directly to current solar wind conditions. Sometimes the magnetosphere acts like a capacitor, gradually accumulating energy from the solar wind until it reaches a threshold where it suddenly discharges in a burst of aurora activity. These releases, called substorms, can transform a quiet arc of green light into an explosion of dancing curtains that cover the entire sky within minutes. The energy stored and released during a single substorm can equal the power consumption of a large city for several hours. The three-dimensional structure of the aurora reveals itself only to observers with the right perspective. From the ground, we see what appears to be a flat curtain hanging in the sky. But the aurora actually exists as a complex volume of space hundreds of miles thick. Different parts of a single display can occur at vastly different altitudes, creating layers of light that photographers sometimes capture as distinct features in their images. Astronauts looking down at the aurora from the International Space Station see this three-dimensional structure more clearly. They describe watching aurora displays that appear as glowing tubes or ribbons snaking through the upper atmosphere, sometimes extending both upward and downward from the altitude where they shine most brightly. These observations have helped scientists understand that the aurora is not a simple curtain, but rather a complex architecture of light, built from intersecting streams of particles following magnetic field lines. The aurora influences the chemistry of the upper atmosphere in ways that cascade through the entire atmospheric system. When high-energy particles collide with oxygen and nitrogen molecules, they don't just create light. They also break apart molecules, creating reactive fragments that participate in chemical reactions impossible under normal atmospheric conditions. These reactions produce compounds like nitric oxide that can survive long enough to diffuse downward into the stratosphere, where they participate in ozone chemistry. During periods of intense aurora activity, these chemical changes can be detected throughout the middle atmosphere, creating a subtle but measurable connection between space weather and atmospheric composition. Hundreds of miles below the aurora displays themselves. The timing of these chemical effects adds another layer to the aurora's influence on Earth's environment. The compounds created during aurora displays can persist for weeks or months, carrying the signature of space weather events long after the visible lights have faded. Scientists study these chemical traces to better understand how space weather affects the entire atmospheric system over time, scales much longer than individual aurora displays. Some of the most dramatic aurora displays occur during periods when the sun's magnetic field briefly connects directly with Earth's magnetic field through a process called magnetic reconnection. When the magnetic field lines carried by the solar wind align in just the right way with Earth's field lines, they can merge, creating a direct pathway for energy and particles to flow from the solar wind into the magnetosphere. These reconnection events can trigger sudden brightening of the aurora that spreads across the sky like ripples on a pond. The lights may begin as a quiet green arc along the northern horizon, then suddenly explode into motion, with rays shooting upward and curtains unfurling across the entire dome of the sky. These moments represent the aurora at its most dynamic, responding directly to changes in the solar wind occurring in real time. The unpredictability of magnetic reconnection adds to the aurora's mystique. Even with sophisticated space weather monitoring, scientists cannot predict exactly when these dramatic displays will occur. The orientation of the solar wind's magnetic field can change within minutes, transforming a quiet night into a spectacular light show, or causing an anticipated display to fade into disappointing dimness. Traditional aurora observers developed techniques for staying comfortable during long hours of outdoor viewing that modern enthusiasts still use today. Layered clothing systems that trap warm air while allowing moisture to escape help maintain body temperature during extended periods of standing still in cold conditions. Insulated footwear becomes crucial when standing on frozen ground for hours at a time. Hand and foot warmers provide localized heat that can make the difference between enjoying an aurora display and cutting the viewing session short due to discomfort. Many experienced observers carry thermos bottles filled with warm beverages, not just for the warmth, but for the comforting ritual of sharing hot drinks while watching the lights dance overhead. The social aspects of aurora viewing often develop naturally as observers gather in popular viewing locations. Strangers become temporary companions, sharing equipment, local knowledge, and the collective excitement when the lights begin to dance. These informal gatherings create a sense of community around the shared experience of witnessing something extraordinary. The aurora has inspired technological innovations that extend far beyond aurora research itself. The sensitive instruments developed to measure magnetic field fluctuations associated with aurora activity have found applications in mineral exploration, archaeological surveying, and medical imaging. The cameras and sensors designed to capture faint aurora emissions have contributed to advances in low-light imaging technology used in everything from astronomy to security systems, space weather prediction, driven largely by the need to understand aurora-producing events, has become crucial for protecting modern technological infrastructure. Satellite operators routinely adjust their operations based on aurora forecasts, moving sensitive spacecraft to safer orientations or temporarily shutting down vulnerable systems during predicted geomagnetic storms. The global positioning system, essential for modern navigation, can experience significant errors during aurora-producing events. The same charged particles that create the beautiful lights also interfere with radio signals traveling between GPS satellites and ground-based receivers. Understanding and predicting these effects has become increasingly important as society becomes more dependent on precision navigation and timing systems. Power grid operators in northern regions monitor aurora forecasts as carefully as weather forecasts, preparing for the induced electrical currents that can damage transformers and cause widespread blackouts during extreme geomagnetic storms. The aurora serves as a visible warning of space weather conditions that can have profound impacts on technological systems throughout the affected regions. The aurora appears in the mythology and folklore of cultures, far beyond the polar regions where it occurs regularly. Even populations that rarely or never see the aurora have incorporated it into their stories and beliefs, often through contact with northern peoples or through accounts of the rare occasions when intense displays appeared at unusually low latitudes. These cross-cultural stories about the aurora often emphasize its role as a bridge between the earthly and celestial realms. Many traditions describe the aurora as a pathway used by spirits, gods, or ancestors to travel between different levels of existence. The lights serve as a visible manifestation of otherwise invisible spiritual forces. The aurora's appearance in creation myths often links it to the fundamental forces that shaped the world. Some stories describe the aurora as the leftover energy from the creation of the universe, still dancing across the sky as a reminder of those primordial forces. Others portray the lights as the breath or voice of creator deities, painting the sky with messages too sublime for ordinary language. Modern interpretations of aurora folklore reveal recurring themes that transcend cultural boundaries. The aurora almost universally represents transformation, communication between worlds, and the presence of forces beyond normal human experience. These themes persist even as scientific understanding replaces mythological explanations, suggesting deep psychological and spiritual responses to the aurora that transcend rational knowledge. The seasonal rhythms of aurora activity align with other natural cycles in ways that create optimal viewing opportunities during certain times of year. The combination of astronomical factors, atmospheric conditions, and solar activity patterns means that experienced aurora watchers can predict not just when displays might occur, but also when viewing conditions will be most favorable. Autumn and spring offer the best balance of darkness and moderate weather in most aurora viewing locations. The sun has moved far enough from its summer position to create sufficient darkness, while temperatures remain tolerable for extended outdoor viewing. These seasons also coincide with equinoctial periods, when Earth's magnetic field orientation relative to the solar wind creates enhanced opportunities for aurora activity. Winter provides the longest nights for aurora viewing, but often brings challenging weather conditions that can limit opportunities to see the light's cloud cover. Precipitation and extreme cold can make aurora observation difficult or dangerous. Despite the increased darkness that would otherwise favor viewing, the relationship between seasonal weather patterns and aurora visibility varies significantly with geographic location. Coastal areas may experience more cloudy nights but milder temperatures, while interior locations offer clearer skies but harsher conditions. Each aurora viewing region develops its own seasonal rhythms based on local climate patterns and their interaction with aurora activity cycles. The aurora creates unique photographic opportunities that challenge conventional approaches to night photography. The constantly changing light conditions require photographers to adapt their techniques continuously, making aurora photography as much about responsive creativity as technical skill. The most successful aurora photographers develop an intuitive feel for how different types of displays will appear in their images. Long exposure times reveal colors and structures invisible to the naked eye, but also smooth out the rapid movements that make the aurora so captivating to observe directly. Some photographers experiment with multiple exposure techniques, combining short exposures that freeze motion with longer ones that capture faint details, creating composite images that represent different aspects of the aurora experience. The challenge of foreground composition in aurora photography has led to the development of specialized techniques for illuminating landscape elements without overwhelming the delicate aurora colors. Photographers use everything from flashlights to controlled light painting to create balanced compositions that show both the lights and their earthly context. Time-lapse photography has become particularly popular for capturing aurora displays, compressing hours of gentle movement into minutes of dynamic motion that reveal patterns invisible to real-time observation. These sequences often show the relationship between aurora activity and other atmospheric phenomena like cloud formation or the movement of weather systems. The aurora serves as a natural timekeeper for cultures living within its range, providing visual cues about seasonal progression and daily rhythms that complement more familiar astronomical markers like the sun and moon. The changing position of the auroral oval throughout the night reflects Earth's rotation, while seasonal variations in aurora visibility mark the progression toward and away from winter darkness. Some Arctic communities traditionally used aurora patterns to navigate across featureless landscapes, particularly during the polar night, when the sun provides no directional reference. The aurora's consistent appearance in the northern sky, combined with knowledge of how it moves throughout the night, provided reliable orientation cues for travelers crossing vast expanses of snow and ice. The relationship between aurora activity and weather patterns, while not fully understood scientifically, forms part of traditional forecasting systems used by indigenous peoples. Changes in aurora behavior sometimes correlate with shifts in atmospheric pressure systems or the approach of storms, though the mechanisms behind these relationships remain subjects of ongoing research. Modern communities in aurora regions often organize their winter social activities around aurora seasons, planning festivals, gatherings, and cultural events during periods when displays are most likely, the aurora becomes part of the seasonal rhythm of community life, marking the return of viewing conditions after the bright nights of summer. The study of aurora has contributed to our understanding of fundamental physical processes that occur throughout the universe, wherever magnetic fields interact with charged particle flows. The same basic mechanisms that create Earth's aurora also produce similar phenomena around other planets, stars, and even in the vast spaces between galaxies, where magnetic fields and particle streams interact. Observations of aurora-like displays around other planets in our solar system provide comparative data that enhances our understanding of how different atmospheric compositions, magnetic field strengths, and solar wind conditions affect these light displays. Jupiter's aurora, powered partly by particles from its volcanic moon Io, creates displays far more intense than anything seen on Earth. The techniques developed for studying Earth's aurora have been adapted for observing similar phenomena in distant astrophysical environments. Radio telescopes can detect aurora-like emissions from brown dwarf stars, while space-based observatories reveal aurora activity around some exoplanets orbiting other stars. These comparative studies reveal universal principles governing how stellar winds interact with planetary magnetic fields throughout the cosmos. Every aurora display on Earth provides data relevant to understanding similar processes occurring on scales ranging from planetary to galactic, making aurora research a window into cosmic physics. The aurora influences local ecosystems in subtle ways that scientists are still working to understand fully. The electromagnetic fields associated with aurora activity might affect the navigation systems of migrating animals, though documenting these effects requires careful study to separate aurora influences from other environmental factors. Some researchers have noted correlations between aurora activity and the behavior of domestic animals in polar regions, with dogs, horses, and cattle occasionally showing signs of agitation during intense displays. Whether these behavioral changes result from electromagnetic effects, unusual lighting conditions, or other factors associated with geomagnetic disturbances remains unclear. The seasonal timing of peak aurora activity coincides with migration periods for many Arctic species, creating opportunities for researchers to study how space weather might influence animal navigation and behavior. These studies contribute to our broader understanding of how organisms detect and respond to magnetic fields in their environment. Plant growth in polar regions might also be affected by the electromagnetic disturbances associated with aurora activity, though these effects would be subtle and difficult to separate from other environmental influences. The aurora represents one component of a complex environmental system that shapes life in polar regions in ways both obvious and hidden. The cultural significance of the aurora continues to evolve as modern communities develop new relationships with this ancient phenomenon. Aurora tourism has created economic opportunities while also fostering greater appreciation for the scientific and cultural dimensions of the lights among visitors from around the world. Educational programs built around aurora viewing combine traditional knowledge with modern scientific understanding, creating learning experiences that bridge different ways of knowing about natural phenomena. These programs often involve collaboration between indigenous knowledge keepers and academic researchers, resulting in more complete understandings of aurora patterns and their cultural significance. The aurora appears in contemporary art, music, and literature as artists find new ways to interpret and express the experience of witnessing these displays. Modern aurora art often explores themes of environmental change, technological impacts on natural phenomena, and the relationship between scientific and spiritual ways of understanding the world. Social media and digital photography have democratized aurora observation, allowing people far from polar regions to participate virtually in aurora experiences while also creating global communities of aurora enthusiasts who share observations, photographs, and knowledge across vast distances. The future of aurora research lies partly in the development of new observational techniques that can capture aspects of aurora formation and behavior previously beyond our reach. Advanced camera systems sensitive to different wavelengths of light reveal structures and processes invisible to conventional photography, while networks of ground-based instruments provide increasingly detailed measurements of the electromagnetic environment during aurora displays. Space-based observations from multiple satellites positioned throughout Earth's magnetosphere provide three-dimensional views of the processes that create aurora, revealing how energy flows from the solar wind through magnetic field interactions to the upper atmosphere, where it finally becomes visible as light. And now, as our gentle journey through the world of the Northern Lights draws to a close, let the last whispers of these celestial facts settle softly in your mind. Like aurora light fading into dawn, we've drifted together through the science and stories, the ancient wisdom and modern discoveries that make the Northern Lights one of nature's most peaceful mysteries. From the solar wind's gentle breath to the magnetic field lines that guide particles home, from indigenous legends to the quiet dance that continues even now above the polar skies, may these soothing truths about the aurora carry you gently into sleep, and may your dreams be painted with the same ethereal beauty that graces our northern horizons night after night, eternal and serene.